Welcome back to educator.com and welcome back to linear algebra. This is going to be lesson number 11 and we're going to talk about n-vectors today. In the last lesson we talked about vectors in the plane, which are two vectors because each vector is represented by two numbers. So when we talk about a vector in 3 space, it's a vector, it's called a 3 vector. We also call it R3, which we'll symbolize in just a little bit. When we speak about n vectors, it's just any number of them. If we're talking about a 10-dimensional space, it just means a 1 by 10 matrix or a 10 by 1 matrix. You remember, it's just 10 numbers. So that's the nice thing about mathematics is you're not tied to what you can represent as far as reality is concerned. It is just as real, but obviously we don't know how to draw a 10 space or an 8 space or a 13 space, but these things do exist and the mathematics is actually exactly the same. So let's get started. Okay, so let's just throw out a few examples. A 4 vector. So something like 1, 3, -2, 6. Again, we're just talking about a 4 by 1. I could also have written this vector as 1, 3, -2, 6. It really doesn't matter. Later on, it will make a difference depending on how we want to arrange it because we're going to be multiplying these things by matrices. So sometimes we want it this way, sometimes we want it this way. Another representation is just regular coordinate representation, x, y, z, so on. So I could also write this as 1, 3, -2, 6. They all mean the same thing. It just depends on what it is that you're doing. Okay, a 7 vector. Let's do. So again, so you'd have 0, 5, 0, 6, 9, 7, 2, something like that. And again, you can write it as a row, you can write it as a list in coordinate form. This just means that you have this many dimensional space. 2-dimensional space is 2 numbers, 3-dimensional space is 3 numbers. This is a 7-dimensional space. Perfectly valid, perfectly real. And the mathematics is handled exactly the same way as it was last time. Okay, let's talk about vector addition. Last time we talked about vector addition when we said when you add 2 vectors together, you're just adding the individual components. In other words, the individual numbers of those vectors together. So let's just do an example. So let's say vector addition. Let's do a 3 vector. So we have 1, -2, and 3. And let's take v as 2, 3, and -3. So when we add them, we're just adding the 1 and the 2, the -2 and the 3 and the -3. And so our u plus v equals, again, it's a 3 vector. 1 plus 2 is 3, -2 plus 3 is plus 1, and 3 minus 3 is 0. So we have the vector 3, 1, 0. If we do scalar multiplication, when we take a vector and we just multiply by a scalar, a regular number, so if I wanted to do, let's use u again. If I want to do 5u, well, I just multiply everything in there by 5. 5 times 1 is 5. 5 times -2, -10. 5 times 3 is 15. So 5u equals, and it's a 3 vector. Nothing changes. We have 5, -10, and 15. So vector addition, scalar multiplication, just like when we did it for vectors in the plane. You just have more numbers. Okay. Now let us write down a theorem. This is going to be a little bit of writing, and again, a lot of this you've already seen before, but it's sort of nice to write it over and over again because it solidifies it in your mind, and it's nice to see it formally in a mathematical sense. Because again, in mathematics, we try to be as precise as possible to leave no room for error. So let's write this one out, and there is one aspect of this theorem that I'm going to digress on, and it's going to be a very important aspect, and you'll see it in just a minute. So we will let u v, w be n vectors, or vectors in n space. We also talk about it that way. So 3 vector are the vectors in 3 space. N space. And just to let you know, the symbol for, let's say, R3, this R here with the double line, it stands for the real numbers, and we put a little 3 up there. It means that we're taking one number from each real number line. If you think of 3 space, you think of it as a z-axis, an x-axis, and a y-axis. So each one of those axes represents the real number line. So since we're using 3 real number lines that are mutually perpendicular to each other, that's where this 3 comes from. So if we talk about n space, it's symbolized Rn. Okay, so let's put a little 1 here, and we'll start with an A. So if we have u, v, and w as n vectors, u plus v is a vector in n space. Well, you know this already. If I take 2 vectors, 3 vectors, and if I add them together, I get a 3 vector. So it's not like I land in some other space. I start with 2, I do something to them called addition, and the result that I get is still a 3 vector. Now, this might seem natural to you, but as it turns out, it's not quite so natural. There are situations, mathematical structures where this is not true, and this is the digression that I'm going to go on in a moment. So when we say that u plus v is a vector in n space, this property is called closure. Okay? And we say that vector addition is closed under addition. So we talk about the property of closure, or we also say that this operation of addition or vectors is closed under addition. And here's what that means. And again, you might think that this is perfectly natural. Why would it be anything else? For example, if I take the numbers 5 and 6, and if I add them together, I get 11, which is just another number. In other words, I still end up with a number. Well, consider this. Let's just take the set of odd numbers, so 1, 3, 5, 7, 9, etc. And let's take the set of even numbers. So all I've done is I've split the number system, the natural number system, into even and odd. So if this is odd, this is even. Now, let's just start with some even numbers. If I take any 2 even numbers, and let's just take the number 4 and the number 8. And if I add them together, so I perform an operation with 2 elements of that set, 8 and 4, I end up with 12. Well, 12 is an even number. So an even plus an even, I end up with an even number. What that means is I start with 2 things, I do something to it, but I end up back in my same set. I don't leave. This is called closure. That means I don't land someplace else. But now try this with the odd numbers. So let's take an odd number like 3, and let's add it to another odd number, let's say 5. Well, when I add these together, I get 8. I get an even number. So I start with 2 elements in this set. I do something to them, I add them, and yet all of a sudden, I end up in a different space. I've separated these 2. Why is it that the even numbers, when you add 2 elements, you don't leave that space, you still end up with an even number, but now if I add 2 odd numbers, I end up outside of that space. I didn't end up with an odd number. This is not odd. So as it turns out, this property of closure is actually a very deep property, and we have to specify it. So as it turns out, when you add 2 vectors together, 2 n vectors, you get an n vector. But this example, this counterexample, demonstrates that it doesn't always have to be the case. That's why it's important for us to specify it. So something that seems obvious in mathematics usually has a very, very deep reason underlying it. That's why we say this. Okay, let's continue. B, u plus v equals v plus u. That means you can add in either order, so vector addition is commutative. C, u plus v plus w equals exactly what you think. U plus v quantity plus w. So vector addition is associative. Okay, D. There exists a unique, remember this symbol, reverse E, it means there exists a unique, that's what that little exclamation, that means there's one, only one. When we say there exists, it could be more than one, but when we say there exists a unique, we're making a very specific statement that it's the only one that exists. So there exists a zero vector such that u plus the zero vector equals the zero vector plus u, commutativity, where you get u back. That is called the additive identity. Identity meaning you start with a vector, you add something to it, nothing changes. You get that vector back. It's an identity. And last but not least, okay, for each u, there exists a unique vector symbolized minus u, such that u plus this minus u vector gives me the zero vector. This is called the additive inverse. Again, 5 plus a negative 5 gives you 0. 5 plus 0 gives you 5. So this zero vector is called the additive identity, and additive because it's specific to this property of addition. Doesn't apply to multiplication. We'll get to multiplication in just a little bit. And for each u, for every vector in n space, there exists a vector negative u, such that when you add them together, you get the zero vector. So they come in pairs. Okay. Now the second part, which actually deals with scalar multiplication. If I take some constant times u, well, that's also closed. So as it turns out, if I have a vector in n space and if I multiply it by some scalar, I end up with a vector in n space. I don't jump to another space. Again, it seems natural, it's obvious, you've been doing it all your life, but there is something deeper going on. It doesn't have to be that way. And as you saw, an example of something that you deal with every day, the odd numbers don't satisfy this property. The odd numbers are not closed under addition. When you add two odds together, you end up outside of the set. You end up with an even, not an odd. So we have to specify closure. It's a very, very important property. So we say this is closed under scalar multiplication, whereas before it was closed under vector addition. Okay, c times u plus v equals c times u plus c times v. So the distributive property under scalar multiplication is active. I can distribute this scalar over the vectors that I add. Excuse me. If I add two scalars together and multiply them by some vector, well, I can distribute the scalar, the vector over the scalars. So it's c, I guess I chose a v here, I meant to do a u, but that's fine. It doesn't really matter. Plus d times v. Okay. And c times d times u equals cd times u. So if I have some vector, I multiply it by a number, and then I multiply it by another one, I can take the vector and I can just multiply the two numbers together and then multiply it by the vector. And again, all of these are very common properties that you're accustomed to. And 1 times u equals u. This one, again, we're talking about scalar multiplication here. Scalar multiple. This one is just the number 1. It is not the vector 1. It is not the unit vector that we talked about before. It is the number 1 times u gives me u back. This is called the multiplicative identity. It is the element that when I multiply by the vector, it gives me back the vector. Nothing changes. Before we talked about the additive identity, the 0, so that when I added it to a vector, I got the vector back. Okay. Let's talk a little bit about coordinate systems. As it turns out, there are two types of coordinate systems. There's something called a right-handed and a left-handed. Generally, unless there is a reason for doing so, it has just been conventional in mathematics to use a right-handed coordinate system. And we'll show what it is that that means here. We'll draw both of them so that you know. Z. Okay. There are going to be times when I forget my arrows. Forgive me, I sometimes just don't write my arrows. Z, Y, and x. Okay. This is a right-handed system. What you've done, notice, x is, so the z and the y are actually in the plane of the paper, and it's as if the, I'll draw this going back also, the x-axis is the one that's coming out towards you and away from you. This is the right-handed system, and the reason it's called right-handed, because if we actually take our right hand and sort of make a little L with this, like this, some people do it with their finger like this. I don't know. I think it's a little less intuitive. Just sort of keep your hand at an angle like that. Your arm ends up being the y-axis. Your thumb is the z-axis. And your fingers are the x-axis, what we would consider like the primary. So once we establish our fingers moving in the direction of the x-axis, the z and the y sort of take this particular shape. Left-handed would be the other way around. And we'll draw that just so you see what it looks like. And this is, of course, in R3. So in 3 space, because we can actually represent it. As you know, we can't represent 4-dimensional, 5-dimensional, or other spaces. So R3 is where we have the right-handed and left-handed systems. Okay, so we have that goes there. That's that. That's that. And all you've done with a left-handed system is switched x and y. So now x and z are in the plane, and y is the thing that comes forward and away from you. And again, x is always your fingers, x, y, z. If you arrange it like this, you'll actually see this is the left-handed system. But again, we're concerned with a right-handed system. This is what we're going to be dealing with primarily. Right-handed. The z and the y are in the plane. It's the x that's coming towards you. It's as if we've taken the xy plane that you're used to and we've flipped it forward toward you, and now the x is pointing towards you and the z is up. Okay. Let's talk about the projection of a point onto a coordinate plane. Very, very important operation. Projection of a point onto a coordinate line or plane, actually, because my first example I'm going to do is going to be a 2-dimensional example so that you can see it, and then we'll do the 3-dimensional. So when we talk about R2, 2 space, we have our xy coordinate. This is x, this is y. That's fine. I don't need to label them. Let's say we pick a point right there, and let's label the point. Let's say it's the point 3, 4. So 3 in the x direction, 4 in the y direction. When I project something onto one of the coordinate axes, it's as if I'm shining a light down that way. And what I do is I drop a perpendicular from that point onto that axis. So I end up at the point 3. If I project this way, if I project onto the y-axis, I end up here, and that's all you're doing with projection, is you're starting with your point, and you're going down to one of your axes, or to the plane, and you're literally sort of dropping off that whatever coordinate you're not talking about. So if I project onto the x-axis, I drop a perpendicular onto the x-axis, and where I end up, this is my projection right here. Now let's do it for 3 space. Okay. When I draw the vector, it's going to seem a little strange, but once I do the projection, it'll be very, very clear what's happening. So these are, we'll label. This is y, this is x, this is z. I have a vector. Okay. Let's say that the vector is 2, 3, 4. Now, I want to project this onto the xy plane. In other words, I just want to shine a light on it and cause I want to see the shadow. That's what the projection is. It's a shadow on the particular xy plane. So I'm going to shine a light on it from above, which means I drop a perpendicular down to the xy, and now from the origin I draw that point. And because I dropped it down to the xy plane, this point is 2, 3. Now we're in the xy plane. The shadow of this vector on the xy plane is that is the actual shadow of that thing. Makes complete sense. You can project it onto the zy plane. You can project it onto the zx plane. In fact, let's do that. If I projected it onto the zx plane, I would have something like that. And you might have perpendicular that way, and then you would have a vector in the zx plane. And that would be, so you take the z and the x, it would be 2, 4. 2 in this direction, 4 in this direction, because now I've ignored the y. Here, I've projected it, cast a shadow onto the xy axis, xy, which means I only take the xy. So I have a vector in the xy plane, which is the shadow, which is the projection of this. Projections are going to be very, very important in linear algebra because, again, anytime you drop a perpendicular to something, you're talking about the shortest distance between something. So the shortest distance between this point and this point is that length. We'll talk more about that in a little bit. Okay, let's move on. Let u be an n vector. So now we're not specifying the space, we're just saying, generally speaking, the magnitude of u is exactly what you think it is. You just take all of the, let's actually list this. So it'll be something like u1, u2, so on, all the way to un, right? That many entries, n entries. So it is going to be u1 squared plus u2 squared plus so on and so on until un squared, all of it under the radical. This is just the Pythagorean theorem in n dimensions. So the Pythagorean theorem was just for u1 and u2. In 3 space, it's u1, u2, u3. In 15 space, it's u1, u2, u3, all the way to u15. Mathematics is handled exactly the same way. Square each entry, add them all together, take the square root. Perfectly valid. Okay, let's see. Let's also define the distance between 2 points. Well, points are nothing but vectors, so we can speak of them as points or we can speak of them as vectors, which is an arrow from the origin to that point. So distance between 2 points. And I know you've seen the distance formula before. The distance between 2 points in vector form is the magnitude. So if one of the points, so if point 1 is represented by some vector u, and point 2 is some vector v, the distance between them is the magnitude of the vector u minus v. In other words, take u, subtract v, you'll still get an n vector, and then take the magnitude of that, meaning apply this. Well, when you write it out, you get, well, u minus v in component form is u1 minus v1 squared plus u2 minus v2 squared plus so on all the way to u sub n minus v sub n squared, and all of this under the radical sign. I prefer to use a radical sign instead of putting parentheses and doing to the power of 1/2, just a personal preference. Symbolism is, I mean, it's important, but ultimately it's about your understanding. So. Okay. So you see that everything that we discussed in lesson 2 for 2 space is exactly the same. It's completely analogous. You just have more coordinates, more numbers to deal with. That's the only thing that's different. And if you remember, we also had another way of representing the magnitude in terms of the vector itself. If we took u, dotted it with itself, and took the square root, that's also another way of finding the magnitude. Okay. Now we're going to discuss a very, very, very important inequality in mathematics. Well, it's profoundly important inequality. It's called the Cauchy-Schwarz inequality, and it might seem a little strange, but it actually does make sense. So I'll put an arrow there. Cauchy-Schwarz. Excuse me. Real briefly, I just want to speak really generally about inequalities, because in a minute we're going to introduce a second inequality called the triangle inequality. And there are many, many inequalities in mathematics. In the branch of mathematics that most of you know as calculus, most mathematicians refer to it as analysis. And analysis is exactly what you think. It's any other kind of analysis. You have a certain amount of data in front of you, and you're trying to come up with some sort of a conclusion for what that data is implying. Well, often you don't really have all of the information at your disposal, so you have to analyze the situation. You're basically breaking it up, seeing what you do have, and seeing how the pieces fit together. Well, as it turns out, really what you're doing is in analysis is you're establishing relationships between the bits of information that you have at your disposal. And relationships, one relation is an equality relation, but in analysis, often you can't speculate about the equality of something, but you can say something about the inequality between those two things. So as it turns out in mathematical analysis, inequalities play a central role because they allow us to order things in a certain way and extract information that way. So analysis really is about dealing with inequalities, relationships among bits of information. So the Cauchy-Schwarz inequality says if I have two vectors u and v, so let's write that out actually. Let u and v be members of Rn, in other words, n vectors, you know. Then, excuse me, the absolute value of u dot v is less than or equal to the magnitude of u times the magnitude of v. Okay, so let's stop and think about this for a second. Let's make sure that our symbolism is understood. A vector with these two double lines, that's magnitude. That's the length of the vector. These are numbers. So if I take the this single line here, it's absolute value. Now, u dot v is a number. It's a scalar. So you can take the absolute value of a number. Sometimes u dot v will be negative. Sometimes it'll be positive. That's why these absolute value signs are here. Well, magnitudes are always positive, so we don't have to worry about absolutes here. What this says is that if I have two random vectors, and if I take the dot product of those vectors, the absolute value of the dot product is always going to be less than or equal to the product of the magnitudes. What this is saying, it's placing an upper limit on what the dot product can be. That's profoundly important. We need to know that we are not just, you know, the number is not just going off to infinity. So it actually places an upper limit on what this dot product can be. It's going to turn out to be very, very important. I'll go ahead and give you an informal justification for this as opposed to an actual proof. I want you to take this informal justification as not with a grain of salt, but take it lightly. This is not a proof. In general, what we do is we end up proving it, and we end up using the Cauchy-Schwarz inequality to, I'm doing something a little backwards. We use the Cauchy-Schwarz inequality once we've proved it to go through this justification to define the angle between two vectors. Now, we did that when we were working in R2. We just gave the definition. However, I'm going to use that in order to sort of justify that this is possible, just to sort of let you know that it is plausible. This doesn't just drop out of the sky. Okay. Remember last lesson we said that the cosine of an angle between the two vectors is equal to u dot v divided by the magnitude of u times the magnitude of v. Well, the cosine of an angle is always between -1 and +1. That's, the cosine curve goes like that. Net positive 1 is an upper limit, negative 1 is a lower limit. Therefore, when I have this negative 1 and positive 1, I can actually write this way and say the cosine of theta, this absolute value signs just allows me to not write it this way, a little shorthand, okay, equal to, so if I take the absolute value of that, well, that's the absolute value of this whole thing, and since the bottom is positive, it doesn't really matter. I don't need the absolute value sign there. Magnitude of u times the magnitude of v is less than or equal to 1. So now I have this thing. Okay. I started with that definition that I had. I know that it's between negative 1 and positive 1, the cosine theta. That means that this value is between negative 1 and positive 1. Take the absolute value of the cosine so that I can eliminate this and just write it this way. Well, the absolute value of the cosine is the absolute value of this thing. Now I have that. Now just multiply through, and what you get is absolute value of the dot product of two vectors is less than, I should probably make this a little more clear here, this is a little odd, is less than or equal to the product of their magnitudes. This is the Cauchy-Schwarz inequality, and this always holds. So again, this is just an informal justification to let you know that this sort of makes sense based on what you know about cosine theta. We actually do it the other way around. Okay, let's move forward. Let's do a little example here. So we said, and this also holds for n vectors, the cosine theta is u dot v divided by the magnitude of u. Whew, writing all these out is exhausting. Okay, so we will let u equal to 1, 0, 0, 1. That's our 4-vector u. And we will let v equal 0, 1, 0, 1. Okay? U dot v, this times that, plus this times that, plus this times that, plus this times that. All of these are 0, so u dot v is equal to 1. The magnitude of u, this squared plus that squared plus this squared plus that squared. 0, 0, these are 1, 1. Square root, radical 2. The magnitude of v, same thing. That squared plus that squared plus that squared plus that squared. Under the radical sign, we get rad 2. Therefore, we have, using this formula, just putting them in, cosine of theta equals 1 over the magnitude of one times the magnitude of the other, radical 2 times radical 2. We end up with 1/2. Cosine theta equals 1/2, and if you remember your trigonometry, theta equals the inverse cosine of 1/2. That is going to be a 60-degree angle, or in terms of radians, pi over 6. So if I have this vector 1, 0, 0, 1, and I have the vector 0, 1, 0, 1, I know that the angle between them is 60 degrees, or pi over 6 radians. Okay. Now, another property, u dot v equals 0 if and only if, meaning it's equivalent to, u and v are orthogonal. In 2 space and in 3 space, orthogonal is the same as perpendicular. But when we're dealing with n vectors, we don't really have a way of visualizing, let's say, 13 space. But we know a 13 vector exists. We can write it. We can do the math for it. It's a very real thing. So we don't use the term perpendicular because that's more geometric as far as the real world is concerned. We use the term orthogonal. So orthogonal is a generalized term for perpendicular. So u dot v is 0. That means that u and v are orthogonal. This if and only if means, well, if u and v are orthogonal, then I know that u dot v equals 0. the implication goes in both directions. That's all this if and only if means. You can also write it as 3 lines. There's an equivalence. This is the same as that. Either one is fine. You can replace this with this with this. Okay. U dot V. When the absolute value of U dot V actually equals, when there is a strict equality of the magnitudes, if and only if U and V are parallel. Well, which makes sense. If you have U this way and if you have V this way, well, the angle between them is 180 degrees. They're parallel. Or the other possibility is U that way and V that way. If they're in the same direction, the angle between them, if I put them right on top of each other, is 0. Well, the cosine of theta is, cosine of 0 is 1. The cosine of 180 degrees is -1. So that's where this inequality in the Cauchy-Schwarz inequality becomes a strict equality. So if I take the dot product and they're equal to 0, I know that they're orthogonal, perpendicular. If I take the dot product and they happen to equal the product of the magnitudes, I know that they're actually parallel. Okay, now let's introduce the other inequality that we talked about. This is called the triangle inequality, also a very, very important inequality. And this one is very, very intuitive because there is a picture for it that you can that makes sense. In fact, those of you that remember from Algebra 1 and 2, you probably spent about half a day deciding whether certain triangles, when they give you the length of sides, is possible. You were doing the triangle inequality is what you were doing. The triangle inequality says, I'll do the algebra, then I'll do the picture. I want to do it the other way around. We're dealing with linear algebra, deal algebraically. Pictures will help us, but it's not, pictures are not proofs. You know, we want to become accustomed to actually letting the algebra do the work for us. It says that the magnitude, and again, U and V are n vectors, the magnitude of U plus V, once I add U plus V, is less than or equal to the magnitude of U plus the magnitude of V. It places an upper limit on the sum of two vectors. The sum of two vectors, the biggest that the sum of two vectors can ever be, is the length of the one vector plus the length of the other vector. Okay? This is an inequality. Here's what this means, and this is why it's called the triangle inequality. Let's draw two vectors. Let's say I have vector U. I'll label it vector U. And let's say I have vector V. Notice I didn't draw them from any frame of reference. They're just random vectors. Adding vectors means you start with one, and then wherever you end up, like for example, you start with one, and then wherever you end up, you add the other one, you just put it on top of it, and you go to that one. The point where you end up, from your original starting point to your final ending point, that's your vector addition. It just means add them in order. Do U first, then do V. So in this case, let's do U, it's here, and V, and then we'll do V, which is here. Okay, so that's V. We end up here. This vector right here is our U plus V. Notice what this says. It says the length of this vector U plus V is less than or equal to the length of this plus the length of this. All that means is that the third side of a triangle is less than or equal to the sum of the two sides. That's all that means. Because if it were longer than the sum of the two sides, what you'd get is a triangle like that. Let's say that's one side. Let's say that's another side. Let's say that's another side. The triangle doesn't close. These will just collapse onto there. In order to have a triangle, the sum of the two sides, sum of any two sides, has to be at least bigger than the third side. Anytime it's equal, well, that situation is just when they basically lay on top of each other. What you have is a line. These collapse precisely to a line. So again, in order to have a triangle, there actually has to be a strict inequality. That's all it means. Once again, the sum of two sides of a triangle is always going to be bigger than the third side. That's the only way a triangle can actually exist. That's why it's called the triangle inequality. As it turns out, it has nothing to do with the pictures. Just because we can draw a picture and we call this thing a triangle, this is an algebraic property. This is true in any number of dimensions. And in fact, it has absolutely nothing to do with a picture. Pictures are our representations of making things clear. This is a deep mathematical algebraic property. Okay. Let's see. Unit vectors. Again, a unit vector is just a vector with a length of 1. And our symbol, my symbol for that, is just x unit. What you do is you take the particular vector you're dealing with, x, and you multiply it by the reciprocal of its magnitude. That's it. All you're doing is taking the vector, dividing it by its length. Just like when you take a number 10, divide by 10, you get 1. Well, you can't divide by a vector, but you can divide by the magnitude of the vector because the magnitude is a number. Okay. In the last section, we introduced the vector I and the vector j. They were unit vectors in the x direction, and a unit vector in the y direction. Now we're going to introduce the unit vector k. It is a unit vector in the z direction. Let me draw my right-handed coordinate system again. Let me darken this up. That is a vector of length 1. That is I in the x direction. That is a vector in the y direction. Call it j. And the vector of length 1 that moves in the z direction is called k. Any vector in R3, 3 vector, 3 space, can be represented as a linear combination of the vectors I, j, and k. In other words, I can take any vector and I can actually write it as a sum. That's what linear combination means. You're just adding of these unit vectors. Very, very important unit vectors. So for example, if I had u equals 0, 4, 2, 3, and let's say I have v is equal to 0, -1, 2, 0. I might say I can write u as 0i plus 4j. Actually, excuse me, let's forget, we're dealing with 3 vectors, not 4, plus 2k. So all I've done is I've taken this vector and I've represented it. That means I move 0 in this direction, I move 4 in this direction, and I move 2 in this direction. And that's all it is. That's all these unit vectors do. They are sort of a frame of reference that allows any vector in R2 or R3 to be represented as a linear combination, as sum of these vectors. We'll get a little bit more into this later when we actually break things up. Okay. Let's see what we've got. Okay, so let's do a little bit of a recap and we'll finish off with some examples. So orthogonal vectors, these are the important points. Orthogonal vectors. When u dot v is equal to 0, if and only if u and v are orthogonal or ortho. So really, really important. Orthogonal vectors, perpendicular vectors, are when the dot product of those vectors equals 0 and the other way around. Cauchy-Schwarz inequality, very important inequality. It says that the absolute value of u dot v less than or equal to the magnitude of u times the magnitude of v. Profoundly important inequality. Triangle inequality says that the magnitude of the sum of u and v is less than or equal to the magnitude of u plus the magnitude of v. Okay, let's do some examples here. Let's let u equal what it is we had before. So 0, 4, 2, and 3. We'll let v equal 0, -1, 2, 0. And I wrote them in coordinate form. Makes no difference. Let's calculate u dot v. U dot v is, you multiply, so 0 times 0 is 0. 4 times -1 minus 4. 2 times 2 plus 4. 3 times 0, 0. 0 minus 4 plus 4, 0 equals 0. So, dot product is 0. So u and v are orthogonal. Let's find a unit vector in the direction of u. Okay, so we're looking for u unit. Well, I know that that's equal to 1 over the magnitude of u times u itself. 1 over the magnitude, that's just a scalar. I'm multiplying the scalar by the vector. Okay, let's see what the magnitude of u is. Magnitude of u equals 0 plus 16. 2 times 2 is 4. 3 times 3 is 9. All under the radical sign. Radical 29. Therefore, our unit vector is 1 over radical 29 times 0, 4, 2, 3. It's equal to 0, 4 over radical 29, 2 over radical 29, and 3 over radical 29. Still a 4 vector, but now this vector has a length of 1. If you were to find the magnitude of this vector, it would be 1. It's in the direction of u, but it has a length of 1. Nice. Okay, let's do one final example, a little bit more complex, sort of tie in some of the things that we did in previous lessons. We want to find a vector v, which is a, b, c, such that v is ortho to both w, which is 1, 2, 1, and x, which is equal to 1, minus 1, 1. Okay, so we have the vectors w, and we have the vector w and x, and we want to find a vector abc. In other words, we want to find abc, at least one, doesn't ask for all of them, but at least one, such that v is orthogonal to both. Well, we know what orthogonal is. Orthogonal means that v dot w is 0, and v dot x is also 0. So let's just use that definition, write out some equations, and see what we get. So v dot w is a times 1 is a, plus b times 2 is 2b, plus c, and we know that that's equal to 0. That's all I've done here. I've used the definition of dot product, and I've written out a linear equation. A plus 2b plus c equals 0. Well, v dot x I also know that it's equal to 0. Well, so v, which is a times 1 is a times negative 1 is minus b, and c times 1 is c. That's equal to 0. Well, I have two equations, three unknowns. Let's go ahead and subject this to reduced row echelon, the Gauss-Jordan elimination, and let's see what we can do. Let's form our augmented matrix here. So 1, 2, 1, 0, 1, 2, 1. Let me put a little thing there so we know that we're dealing with the zeros over here. And 1, negative 1, 1. We're going to subject this to reduced row echelon form. And when we do that, we end up with the following. We end up with 1, 0, 1, 0, 0, 1, 0, 0. This is reduced row echelon. This first column is A, the second column is B, this one is fine, this one is fine, this one, this is not, there's no leading entry here, it's free, so as it turns out, this third variable C can be absolutely anything. Therefore, our solution is the following. C equals anything. Well, B equals 0. That's what this does. It allows us to just read off what's there. So B plus 0 equals 0, so B equals 0. And now A is equal to, well, actually, let me write it differently. A plus C equals 0, therefore A equals negative C, or negative anything, because I can choose anything for my C. So let's just say that C equals 5. That means B equals 0, and A equals negative 5. So one possible answer is negative 5, 0, 5 for my vector V. This vector is orthogonal to that vector and that vector. And again, C can be anything. So it's not the only vector. There's a whole slew of vectors. It's an infinite number of them. So this has an infinite number of solutions. And what we did is we just used the definition of dot product, and we used the fact that we know that anytime two vectors, when they're dotted and it equals 0, they're orthogonal to each other. Okay. Thank you for joining us here at educator.com, Linear Algebra. We'll see you next time.